regions obtained for the abnormal images, and we have compared this with our normal images. You can see there is a quite discrimination in the result between the normal images and the abnormal images. So we have further applied the classification technique. We have used the k-nearest neighborhood classification technique, and with this the accuracy of the proposed method, even though it is not so good, it is 90% for abnormal images and 90% for the normal images. So then what we did later, we used the curvature technique again here, and you can find this is a active contour, and we have segmented the image based on the active contour, and then we obtained the largest curves and the curvature we have obtained. So we have analyzed based on this for the normal and abnormal images. This is the one curvature for normal images. I think it must be abnormal image, and this is the curvature profile. And these are the comparison of results for 5 abnormal and 5 normal images. So here also you can find, even though it is not so effective technique, but still it can come out with a good result for abnormal images. And even there are equal number of curvature you can find, there are a little bit lesser number of curvature, zero crossings in the normal images. So these are classification results. We have used nearest neighborhood classification and KNN classification techniques. So nearest neighborhood classification provided us 96% accuracy, whereas KNN given us 98% accuracy for abnormal. For normal images it is 90% each for both the techniques. So later we moved on one more technique, that is graph based technique. Graph is extensively used for image segmentation. There are plenty of graph based techniques that are being developed in the image processing area. Few graph based techniques we have adopted, and later I have worked on this area also after PhD also. So this is whatever the work I have just done during the PhD, I am just presenting them. So one technique called as graph cut based active contours. So this technique, this is a combination of active contour and graph technique. This technique we have used for our images. So basically in the graph based techniques, image is treated as a graph. Basically what the image contains? Image contains pixels, okay, and these pixels will have intensity. So when we take up the image, every pixel is treated as a vertex, okay, a point, okay. Every point or pixel is treated as a vertex, and every pixel will have a neighboring pixel, and there will be a difference in the intensity between one pixel and its neighboring pixel. The difference in the intensity is treated as a edge. Suppose one pixel is having intensity 100, another pixel is having intensity 105, then edge between both of them is 5. Okay, difference in the intensity. If both pixels will have same, then the edge distance, that is the distance between them, will be 0. Okay, that is edge value will be 0. So basically it is a kind of weighted graph where the vertex, the relation between every vertex will be weights. It will be measured in the form of weights. So in contrast to the framework of active contours, graph cut approaches are applied as a global optimization methods for computer vision problems like image segmentation. See, these graph based techniques are used when we want to focus on the global property of the image instead of focusing on the regional property of the image. Why? Because the whole image is treated, whole image itself will be treated as a graph. The graph cut based active contour image is in GCP-AC, image is represented as graph using adjacency. So just now I told you how we are representing it. So let us see what we have in this. Directly move on to the results. Okay. So in the graph technique, directly it focuses on the region which is being under the extraction. So you can see these are the abnormal images, and it has extracted the abnormal region from these images. So it's a segmentation technique, one such segmentation technique. It has extracted most of the abnormal regions from the image. The advantage of this technique is it is computationally inexpensive. As compared to the active contours, the graph cut based active contour technique is computationally inexpensive, and its computational complexity is of order n to the power 1 by 1.2, almost n, okay, of the order n. So it's a very fast technique, okay, it uses the minimum kind of data structure while implementing the technique. So these are the advantages of the graph cut based active contours. Later we evaluated the performance of all these techniques. We compared all these techniques, we have evaluated which technique is better for what kind of images, and based on time complexity, then segmentation accuracy, time complexity, space complexity. Three parameters we focused on while evaluating the technique. And what we did, we took the images with 1%, that is 0% abnormality, 1% abnormality, 2, 3, 4, up to 40% abnormality. We selected images with different percentage of abnormality, and then we applied the segment, we checked the segmentation accuracy of all the techniques, we checked the time requirement for all these techniques, we checked the space complexity, how much space it occupies, memory space while running, while execution, how much memory space it occupies, that also we have checked. Then we have used some 3 watershed segmentation based techniques. We separately tested their performance for them. Then I will just focus on their advantages, all these techniques, advantages and disadvantages, and some of the applications we will look at. So as I told you, manually we obtained the segmented images with the malignancy, that is abnormality in the images with 1% to 40%, 1 to up to 40%, and compared with the automatic, that means these we have compared with the automatic, our proposed segmentation technique. The as I told during that time we had a very slow computers. We used a Pentium 3 computer with 500 megahertz and 128 MB RAM. Very slow computers, right? So if we just compare the segmentation accuracy, so here the percentage of the malignancy, that is abnormality, manually when we obtain. So how much it could when we perform the same by applying the proposed technique, what is the result we got? How much was the accuracy of the results? You can see the curves are almost like this. Most of the curves, almost all the curves are like this, and this shows that our the manual technique and our proposed techniques are almost matching. Okay, how much is the malignancy or how much is the abnormality in the manual image? That means how much we have obtained through physician's help. So it matches with the proposed techniques. So if we analyze just this RGB, there like you can find different colors are shown for these. You can see this is the RGB, then HSI, watershed segmentation, RGB and watershed segmentation, HSI and watershed segmentation, graph cut based active contours and active contours, normal active contours. So these are different graphs, and if we just compare them, these results, RGB segmentation and active contour segmentation and the graph cut based active contours. So these algorithms are very close to the manual segmentation, okay, as compared to the other techniques. In case of watershed segmentation method and segmentation using active contours without edges, the proposed algorithm fails to segment the abnormal region when the percentage of malignancy is less than 5%. You can see here, in some regions over here, this is it has a badly failed. Some of the techniques have badly failed when the malignancy is less than 5%. In all cases, there is a proportionate matching between the normal segmentation and segmentation performed by different proposed methods. So this is evident because almost all the curves are moving towards higher end as the malignancy increases. So when we come to the time complexity, how much time each and every algorithm took for execution, you can see almost all techniques are independent of the amount of abnormality present in the image. With the variation in the malignancy, with the variation in the abnormal region in the image, almost all techniques require same time to segment the abnormal region. But whereas there is one technique, that is, I think it must be graph cut based active contour, with the increase in the amount of malignancy, with the increase in the amount of abnormal region, it requires more amount of time. Why? It is because it starts deformation, and as the region increases, it will go for more and more number of loops. more and more number of iterations. So it is not hard at lesser number of iterations. So I think that must be the reason why the time required for active contour based segmentation is more. So in case of graph cut based active contours, the time required for segmentation is proportionally changing with the variation in the area covered. So that we have seen. The segmentation by active contours without edges require very large number of, one technique we have not covered here, that is active contours without edges. So you can't find here active contours without edges because to conduct one segmentation, one image segmentation during that time, it required almost half an hour to 45 minutes. That much time was required for this technique. Of course, now we have very fast computers. It may require maybe 2-3 minutes. But still, it is a very high time. Okay, the time complexity is very high. So as compared to, these are measured in seconds, but that technique we have to measure in minutes. So that's why it is not included in the graph. It is highly, as I told you, it is computationally very extensive technique. So average time required for that technique, active contour, is 184 seconds. Okay, so as compared to the other techniques, also the time required here is independent of, okay, so in that technique, in most of the techniques, the time required for segmentation is independent of the abnormality except one technique. Right. Now let us analyze the space complexity. How much space is required for memory space is required when we are executing these techniques. So you can see almost all the techniques require lesser space, that is in KB around 2 MB maybe. Okay, 2000 KB means it must be 2 MB. Almost all techniques require less than 2 MB, but only one technique requires very high memory, that is graph cut based active contours. It is because the whole image is treated as a graph and we are establishing the pixel to pixel relation, we are measuring the weights of the graph, so that is nodes. So for that reason the memory required is really very high. So from the bar graph it can be noticed that the graph cut based active contour algorithm needs relatively large amount of runtime memory space. So it's almost 12 KB as compared to other techniques which require 2 MB, 12 MB and 2 MB. It is because the integral calculations in this algorithm are usually the bottleneck in terms of computational complexity of the curve evolution. So the reason we are using integral calculations. So for that reason it is highly space complex. Here an image is of size, an image is of size need to calculate and keep in memory about dissimilarity. The segmentation by active contours without edges require lowest amount of runtime memory of its implementation. There is one technique, okay, so this is active contours, so that requires very less memory space while running this technique. Okay, then we have compared 3 graph that is watershed segmentation based techniques, because based on the watershed segmentation we adopted, that is normal watershed segmentation directly on the image, then RGB segmentation followed by watershed segmentation, then HSI segmentation followed by watershed segmentation. The performance of RGB in combination with the watershed segmentation is quite good as compared to the other technique. Okay, so this is what we can find from this results. So now let us move on to, I will just brief what are the advantages of these techniques and what are the disadvantages of these techniques. The two algorithms, namely RGB segmentation and graph cut based active contours, are advantages for segmenting the image containing tumors and cancer growths. So based on the entire work what I have carried out, I came out with certain observations. So whenever I am focusing my work on tumors or cancer growths, two techniques are very effective. That is, one is the RGB segmentation and another one is graph cut based active contours. The graph cut based active contour globally locates the contour and the similarity region from the segmentation whereas RGB segmentation algorithm segments based on color properties. So the discrimination among these two techniques. The other algorithms can be advantageous in segmenting any kind of abnormality in the region. So if we are focusing on any other abnormality other than the tumors or cancer growth, then you can go for other techniques also, they are advantageous. The algorithm based on active contours without edges expands the initial contour and breaks it into many regions depending on the local pixel properties of the image. It may be advantageous to segment images containing abnormalities spread all over the image. See, one important property of active contours without edges is that if we have multiple abnormality in a single image, then this technique is very useful because it spreads itself